Welcome back to the channel. In today's video, we will be discussing how we evaluate the shear stresses, and hence establish the size of welds in built-up beams. We have been interviewing newly graduated engineers for a while, and we've discovered that the majority of them struggle with this topic. Any beam formed by connecting more than one component is dependent on the quality of the fixing between the components for its strength. A laminated timber beam, for example, is made up of 4 separate strips of wood. When a load is applied, if the strips are smooth and unconnected, the beam will deform. In effect, it behaves like 4 independent shallow beams. On the other hand, if the laminates are securely glued together, it deforms like a unified deep beam, which, in this case, is 4 times stronger and 8 times stiffer than the unconnected beam. The glue is necessary to transmit horizontal shear stresses from one laminate to the next. However, if the shear stresses are greater than the glue's strength, the glue will fail. So how can we evaluate these shear stresses, and hence establish required strength for the glue? This equation can be used to calculate the shear stresses acting on the cross-section. The derivation of the equation is not covered here, but it is based on considering the equilibrium of stresses acting on a small element within the beam. The equation assumed that the shear stress is constant across the width b of the cross-section. So tau is a function of the distance along the beam in the distance above the neutral axis y. V is the shear force acting on the cross-section. B is the width of the cross-section. It can vary with the distance y from the neutral axis. I is the area moment of inertia, which is a constant value calculated based on the shape of the cross-section. And capital Q is the first moment of area for the portion of the cross-section above the location we want to calculate the shear stress for. So, it varies with the distance y above or below the neutral axis. It is equal to the product of the area above the location of interest in the distance between the centroid of that area and the neutral axis. If the point of interest is below the neutral axis, the area below the axis is taken into account rather than the area above it. The shear flow equation is the next equation, which is useful in built-up shapes, and can be used to determine the size of welds in built-up beams, as well as the spacing of individual connectors such as bolts, rivets, and nails. Shear flow, Q, is defined as shear force per unit length, and it equals shear force, V, multiplied by the first moment of area, capital Q, divided by the moment of inertia, I. Let's look at a real-world example. A 203 by 133 by 30 universal beam S275 is strengthened by welding a steel plate 250 mm wide and 10 mm thick to its top flange. The composite section is subjected to a design shear force of 350 kN. What size continuous fillet weld is required between the beam and the plate? First, we need to determine the section properties. Determine the neutral axis's location, and the moment of inertia I of the entire cross-sectional area about the neutral axis. To make things easier, we'll build a table to help us record our findings. We have a plate, and we have a steel beam. What we need to do is to find the areas for each of these. The area of the plate is the width 250 mm, times the thickness 10 mm. This gives us a value of 2,500 mm squared. The area of universal beam, 203 by 133 by 30, is 3,820 mm squared. You can find the dimensions and properties of the beam in the Blue Book Steel Universal Beam Table. So, if we sum those up, we are going to get 2,500 plus 3,820, that is total area, 6,320 mm squared. In the following column, we must calculate yn, distances between the centroid of each area, and the bottom y-axis. For the plate, yn equals half the plate thickness 10, divided by 2, which is 5 mm, plus, the height of universal beam, 206.8 mm. This gives us a value of 211.8 mm. For the steel beam, yn, distance equals the half of the beam height, that's 206.8 mm, divided by 2, which is 103.4 mm. The following column is area multiplied by yn. For the plate, area 2500 times y 211.8 mm, which is 529,500 mm3. For the steel beam, area 3820 times yn 103.4 mm, which is 394,988 mm3. When we add these up, we get a total of 924,488 mm3. Therefore, the location of neutral axis, y bar equals 924,488, divided by the total area, 6,320. This gives us a value of 146.3 mm. In the next column, we need to find y, the distance from neutral axis, to the centroid of the member's cross-sectional area. For the plate equals yn 211.8 mm minus y bar 146.3 mm. This gives us a value of 65.5 mm. For steel beam equals y bar 146.3 mm minus yn 103.4 mm. This gives us a value of 42.9 mm. Next column is area y squared. For the plate equals 10.7 by 10 to 6. For the steel beam equals 7 by 10 to 6. We sum these up, gives us a total value of 17.7 by 10 to 6. In the last column, we input our moment of inertia of both the plate and steel beam. For the plate, the moment of inertia equals 250 times 10 to 3, divided by 12. This gives us a value of 20,833 mm to 4. For the steel beam, we have already found from the table, which is 29 by 10 to 6 mm to 4. We sum these up and we get 29.021 by 10 to 6 mm to 4. Therefore, the moment of inertia about neutral axis equals total moment of inertia 29.021 by 10 to 6 plus total AY squared 17.7 by 10 to 6. This gives us a value of 46.72 times 10 to 6 mm to 4. So, now we should be able to work out the shear flow and determine the required fillet weld. V is the shear divided by 2 because we have 2 welds, so 350 kilonewtons divided by 2 equals 175 kilonewtons. Capital Q is then equal to the area of the plate, 2,500 mm squared, multiplied by the distance from the neutral axis to the plate's centroid, 65.5 mm. This gives us 1.64 by 10 to 5 mm to 3 as a value. We've already calculated the moment of inertia for the entire section to be 46.72 by 10 to 6 mm to 4. Therefore, the shear flow equals 0.62 kilonewtons per millimeter. Finally, let's look at a 6 mm fillet weld. The strength of fillet weld of leg length 6 mm, for S275, equals 0.163 times 6 mm. This gives us a value of 0.98 kilonewtons per millimeter, which is greater than 0.62 kilonewtons per millimeter. Therefore, a 6 mm fillet weld is deemed satisfactory. Thanks for watching. We hope you found some useful tips. Check out our website at structuralengineercalcs.com. Please like and subscribe, and let us know what would you like to see next. The human footprint is a masterpiece of engineering and a work of art. Stay safe. Goodbye, and see you soon.